So good day everyone. So we are the group 3 and we have chosen case scenario 3 as our topic, which involves designing a better playground with safe and fun swings. So our tasks for today are as follows. First is calculate the mean, variance, and standard deviation of the periods. Second is utilize linear regression to determine the spring constant based on the relationship between mass and the square of the period. Third is discuss the accuracy of the spring constant and possible sources of error. Fourth is explore Hooke's law, harmonic motion, and the derivation of the spring constant. Before delving into this task, I will introduce first our top chosen topic, which is case scenario 3, designing a better playground, safe and fun swings. So the local community is planning to build a new playground and they want to ensure that the swings are safe yet enjoyable for children. They need to determine the appropriate spring constant for the swing to ensure they are neither too stiff nor too loose. So the city council is looking to design the perfect playground for kids in your neighborhood. Your group is tasked with determining the ideal spring constant for the swings, ensuring that they are fun and safe for all ages.
But before we continue, let's talk first about Hooke's law. So, what is Hooke's law? As a formula, it reworks Hooke's law and is expressed through the equation K equals negative F over X, where K is the spring constant, F is the force applied over X, and X is the displacement by the spring expressed in M over M. Hooke's law is a principle of physics that states that the force needed to extend or compress a spring by some distance is proportional to that distance. This can be expressed mathematically as F equals negative Kx, where F is the force applied to the spring, either in the form of strain or stress. X is the displacement of the spring. But for a better understanding of Hooke's law, this video best describes the law. So let's watch this video.
It'll be on the video, and you can go back and rewatch this. So here I have a spring, and I want to find the stiffness of the spring two ways. And in both those cases, I'm gonna make a graph. Okay, so first thing I'm gonna do is just collect some data. The first data, I'm just gonna stretch the spring and measure the mass in the stretch. Okay, so I should say, if I put a mass on here, it has a mass m, then the spring pulls up with some force F spring, gravity pulls down mg, and if it's at rest, then those two are equal. So F spring, the magnitude, is going to be equal to mg. So whatever the weight of this is, that's the spring force. And then I do also know the spring force model, the magnitude of that is going to be k times the stretch. Okay, so that's important. So if I know that the stretch and the force are proportional. So let's get to it and start taking some data. I have my little data table here. I have a little mass. I'm going to hang it here, and I'm going to measure the position. And you're like, oh, I need the stretch. No, you need the position. So I'm going to measure from the top right here, and I'm just going to get a rough estimate. It's moving a little bit. I'm going to say 50.5. I'm going to try to do this fast. 50.5. This is in centimeters. Okay, so there's your data. It's not perfect, but it's good enough. So we're going to make a graph to find the spring constant. I'm going to do that in a second. Let's collect some more data. So the other thing is if I take this and I oscillate it, it turns out the period of oscillation, the time it takes to go from here back to there, one complete oscillation is t equals 2 pi square root of m over k. That's the period of oscillation. Okay. So I want to collect data so I can again, I want to collect period and mass data so I can again make a graph to find k. And this is the part that everyone has trouble with, so I'm going to show you that. Okay. So, but I need that data. And now in order to get this data, I'm actually going to measure 10 oscillations and then divide by 10. Okay, so I already have here 270, and I'm not going to do all these numbers because I'm too lazy. So this is here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.53. Okay, so I could do this a lot better, right? I could actually do a video analysis of this or use some other better methods for this, but you know, this is just really quick and simple. So now what I'm going to do is I'm going to make two graphs. The first graph, I'm going to find the spring constant from this data, and the second graph, I'm going to find the data from this. So you might want to write down that data and do it yourself, but I'm going to do it for you, and we'll switch to the computer. So I've put my data from the board into the spreadsheet. I like to put things in a spreadsheet first before I plot them, because that way I find it easier to change the numbers in ways that I need to. So let's do that. So the first thing I want to do is get the mass in terms of kilograms. I'm going to say M in terms of kilograms, and that's just going to be equal, and I can say equals this divided by 1,000 right there. And I can copy that down. Next, I'm going to get Y in terms of meters. Again, I can just say that's equal to this divided by 100. Copy that down. And then finally, I need the period in seconds. And I recorded the period for 10 oscillations. So that's going to be equal to this. Actually, let's just not do that one. That's going to be equal to this divided by 10. And then copy that down. Okay. So now let's go ahead and make a graph for this first thing. So I'm going to copy this data right here, mass and position. Okay. And let me look over here. Where did I put it? Right here. So this is the formula I'm dealing with. So if I plot, if this is like, let me just add the equation in here. Let's just say, remember this, just to be clear. Okay. I'm editing this for you. Let's say y equals mx plus b. This is my equation for a line. So if I plot the force on the vertical axis and I'm going to actually plot position on the, not the stretch, on the x-axis, then the slope should be k. So let's do that. I'm going to use, this is Logger Pro. We use it to collect data, but you know, you can use this for graphing too. So I'm just going to paste my data in there. I'm going to go ahead and edit these columns because I want to make them look nice. So this is the mass, and the units are kilograms. This is going to make things look nicer. And this is Y. I'll leave it as Y. Just double click on that. And it's units of meters. Okay. Okay, so now I want to plot. The first one I want to plot. Oh, crap. Sorry. Okay. Go back over here. I actually don't need the mass. I need the force. So let's say F equals, it's going to be this mass times 9.8. I should have done that before. No wonder it wasn't looking right. Okay. And that's in Newton. So I'm going to copy that down. And then I'm going to put that in for the, instead of the mass. So I'm going back over here to Logger Pro. Where do I even put it? There. So, and that's going to be force. Okay. So I want to put the force right here versus the stretch. Okay, that's good. And then I'm going to zoom in. There we got a line. Now I'm going to fit a linear function to that, and there you go. Boom. Okay, so here I get the slope is negative. It should be, because remember I'm measuring up, but it doesn't really matter. So I get 7.609 newtons per meter. So I get this, that's my spring constant right there. That's pretty nice. That's a pretty linear fit. I didn't even do a great job, right? Okay, so let's just save this. Let's just save this somewhere. That's fine. Spring 1. Okay, now let's make a new graph. And what are we going to plot? So now I want to deal with the period of oscillation. So if I come back over here, this is my expression for the period, 2 pi squared to k over m. That's not a line, right? That does not look like this. I can't plot t versus something. I don't know what I even plot, okay? Actually, I got this backwards. Okay. This is wrong. Okay, wait 1 second. So, I wrote it wrong on the board too. I'm having a wrong day today, that's for sure. Okay, let's just double check. It's m over k. I wasn't thinking when I wrote that. It's early. Okay, so that changes this one. M over k. And that changes this one. Okay. That makes more sense, because as I increase the mass, it takes longer to oscillate. Okay. If I had a stiffer spring, it'd take less time to oscillate. So here's my t is not proportional to the mass. They're not linear, right? It's not t and something times m, because it's the square root of m. So if I get rid of the square root, that might work. So if I square both sides, I get t squared, 4 pi squared m over k, and I can write that as t squared times 4 pi squared over k. All that stuff's constant times m. So I want to plot t squared versus m, and that should be a straight line, and that should be my slope right there, not k. Okay, so let's do that. So I need to calculate t squared. I'm going to go back over here to my spreadsheet and say t squared. And that's just going to be equal to this time. Actually, again, skipping that one. It's going to be equal to this time. squared. And then copy that down. Okay, so I'm going to copy all of that. Let's just copy the masses again. I'll skip these. Actually, I want the mass in kilograms. I'm going to skip that first one because I didn't do it. And go to my Logger Pro. This is the mass. M kilograms. And then I'm going to copy my t squared. And the reason that we do this, the reason we want it as a line is so that I could do it on graph paper too. And this is going to be t squared, second squared. Okay. And then so it's t squared versus m. That's where I want it. Let's zoom in. It's fairly linear-ish. It's not as great. Oh, I didn't. Let's see. Let's highlight all of this data. Make a graph. Get rid of this one. Okay. So from right there, I get a slope of 4.54. Okay. So that's not the spring constant. So let's go over here, and I'm going to write that down. So let's say slope 4.54. That's right. Okay. And now if I go back over to my calculations, that slope is 4 pi squared over k. So k would be 4 pi squared over the slope. 4 pi squared over the slope. So let's go back to my calculation and say k equals 4 times pi squared divided by this number. And I get 8.9, which is different than what I had before, but it's in the same ballpark. And I didn't take a very good experimental measurement of that. I was really kind of rough, especially with the timing. You can do a lot better job. But there you go. I found the spring constant 2 different ways, and I made 2 different graphs, and they were both linear, and that made me happy.
As for the equations, I'll be explaining the steps as to how to calculate the mean, the variance, and the standard deviation of the periods. But firstly, what is our goal? Our goal is to determine the appropriate spring constant for playground swings. So basically, in this experiment, I will appropriate spring constant for playground swings to ensure that they are both safe and enjoyable for children. In this data set provided, it consists of 5 different masses, which are 0.1, 0.2, 0.3, 0.4, and lastly 0.5 kilograms. And their corresponding oscillating periods are 0.63, 0.89, 1.09, 1.26, and also 1.41 seconds. Now, how do we get the mean? To get the mean period, we firstly add all the periods and divide them into how many numbers of periods, which is 5, which equals to be 1.056 seconds. Second is to get the variance. You firstly have to calculate the differences and repeat for each period. Sum up the squared differences between for each period, which is denoted as xi minus x, then square those differences and period for each period, summed up the square differences, then divide the sum by 5, which equals to 0.0754. As for the standard deviation, it is the square root of the variance, which basically means square root 0.0754 equals to 0.2746 seconds. Next is the linear regression. A linear regression was then applied to explore the relationship between the mass of the swing and the square of the period t squared. The squared periods were calculated as 0.3969, 0.7921, 1.1881, 1.587, and lastly 1.9881. And the regression analysis revealed a slope of 3.9779 and an intercept of negative 81 times 10 to the power of negative 3.
Calculate the mean. First, you take all the periods from your dataset and add them together. For example, our periods like 0.63, 0.89, 1.09, 1.26, and 1.41 seconds. You would add those numbers to get a total. Next, you count how many periods there are. In this case, there are 5 periods. And lastly, you divide the total sum of the periods by the number of periods. This gives you the average or mean. Calculate the variance. For each period, subtract the mean from the period's value. Next, you square each of those differences. Squaring makes sure that all the values are positive and emphasizes larger differences. After that, you sum all those squared differences together. This gives you a measure of the total spread of the periods around the mean. And last, divide the total of squared differences by the number of periods. This gives you the variance, which measures how much the periods vary from the mean on average. To find the standard deviation, simply take the square root of the variance. The standard deviation provides a measure of spread that's in the same unit as the original periods.
Now, we need to find the linear regression of the spring constant from the relationship of the mass and the square of the period. Before we do the formula, it's better to have a table so that we can substitute later on. Here we have our x, which is our mass, our y is the square of the period, xy is mass multiplied by the square of the period, and x squared is mass squared. So that we can fill out our table and we can find the total of our x, our y, our xy, and x squared. So here's the formula to find the linear regression, which is y equals mx plus b. But we need to find m, or the slope, and b. To find m, we can just substitute using the formula given, which is 5 multiplied by 2.18363 subtracted by 1.5 multiplied by 5.9528 divided by 5 multiplied by 0.559 subtracted by 1.59 squared. Then we group these numbers and we have our answer, which is 3.974. To find our b, we already have our m and the given from the table, so that it will be 5.928 subtracted by 3.974 multiplied by 1.5 divided by 5, which we get 2.81 multiplied by 10 by the power of negative 3. So here we have our m over b. So here we have our linear regression. We can just input from what is given earlier from our plotted dots. Our x is our mass and our y is the square of the period. So that we can just input our first dot, our second, third, fourth, and fifth from the table that was given earlier. And we can put our best line or best fit. So how do we find the spring constant? So the formula to find the spring constant is by using to find the period. But how are we going to separate from the spring constant? First, we have to divide both sides by 2 pi to cancel, then square both terms so that we can remove the square root from m over k. Next, we need to separate the spring constant, so that will be equals to m divided by t squared divided by 4 pi squared. But we need to put it at the numerator, so that it will be 4 pi squared multiplied by m over t squared, which will have 4 pi squared divided by t squared multiplied by m. Our 4 pi squared divided by our t squared is equals to our slope, and our slope was 3.978. So that means if we have 4 pi squared over our slope, that will be our spring constant. So that means k equals 4 pi squared divided by 3.9779 is equals to 9.8244 newtons per m. So how are we going to find the accuracy? Actual observation from earlier was 9.92 newtons per m. So we need to have our periods and masses. We need to find the spring constant of each term. We have 5 from the first until the fifth. So that means we have to use our first period and first mass, second, third, fourth, and so on. So here we have our first period and our first mass given by using the formula of the To find our spring constant, we get 10 n over m. Then to find the absolute error, we have to subtract by the observed subtracted by our actual but inside the absolute, which is 0.08 n over m. And then we need to find the percent of error. The formula for it is the absolute error divided by the actual observation multiplied by 100%, which we get 0.81%. And our percent of accuracy is 100% subtracted by our percent of error earlier, which is 99.19%. So before we move on, here are just our terms so that you won't be confused. T is our period, K is equals to spring constant, our M is our mass, absolute error is absolute error, and A is our actual observation. Then we have our second period and our second mass that has been given. Our spring constant given is 10.21 n over m, and then our absolute error is 0.29 m over m. Percent of error 2.92%, and our percent of accuracy 97.08%. Then from our third period and our third mass, it's already given using the formula. The spring constant is 10.38 n over m. Our absolute error is 0.46 n over m. Percent of error is 4.64%, and our percent of accuracy is 95.36%. And our fourth, using the same formula, is 10 n over m. Our absolute error is 0.08 n over m. Our percent of error 0.81%, and our percent of accuracy 99.19%. Then our fifth, our last mass and period given, our spring constant using the formula is 10.33 n over m. Our absolute error 0.41 n over m. Our percent of error 4.13%, and our percent of accuracy 95.87%. So to give a more observation of our terms, we could just use to find the percent of difference. From our percent of difference, we are using the spring constant of what is been given earlier. Remember of what we used our spring constant from the previous slides to find the accuracy. We can use that for the percent of difference. So as you can see, the formula to find the percent of difference is equals to absolute x1 minus x2 divided by 1/2 multiplied by x1 plus x2, then multiplied by 100%, which is already given. So we actually use our spring constant from the previous slides to find the percent of difference. And as you can see, we input the numbers of what is needed so that we can find the percent of difference.